So question 2 is a little bit interesting because it only involves understandings of limits. You most likely won't be asked a question that's exactly like this, but the concepts that you use in this are going to be really important. So we have a function which we don't know what a is, we don't know what b is. They tell us that we have a horizontal asymptote at y equals 3, and they also tell us that f has a removable discontinuity at x equals 2. So first thing I want to do is talk about the horizontal asymptote. If you have a horizontal asymptote, actually by definition of what a horizontal asymptote is and what a limit is, that means that the limit as x approaches infinity of this function is going to be equal to that horizontal asymptote. So that's the first thing that you need to notice. The second thing is noticing what the limit as x approaches infinity actually means. So if you notice that we have our top term in the numerator and the denominator, our leading term, has a degree of 2. Since we have the same degree in our numerator and our denominator, we're going to look at the coefficients of that top term. That actually is going to be equal to that limit based on the definition of limits at infinity. If you don't remember that, I recommend that you go back and review it. So because we know that the limit as x approaches infinity is equal to 3, and we also know that it's equal to those two coefficients, that shows us that a is equal to 6. So that's our first thing that we have. Actually, for full credit on this problem, you need two things. You need, or for this part of the problem, this right here will give you a point. Also, getting this a over 2, that's going to give you the second point. So the next thing I want to talk about is that removable discontinuity. A removable discontinuity on a graph, if you remember, it's going to look like this. It has like an open circle. There's a hole in the graph. What that means is that you're just missing one point. Actually, though, the limit at that value is going to be defined. It's not going to be non-existent. So that's what's going to happen in the graph. With the equation, you're actually going to have both the numerator and the denominator being equal to 0 at x equals 2. So that's where if you remember the indeterminate forms, like the 0 over 0 forms, come in. Usually when you have an indeterminate form, you're going to be able to simplify, you're going to be able to factor and cancel stuff out. That would be what would happen in this case. So numerator and denominator equals 0 at x equals 2. You can probably check that with the denominator. You'll notice that if you plug in 2, you do get 0. We also want our numerator to be equal to 0 when x is equal to 2. So I'm going to go ahead and show that. Actually, we already verified that a was equal to 6, so we can use that. So from there, you can just solve for b now. And hopefully if you solve for b, you end up getting that b is equal to 13. Sorry, negative 13. So in this one, doing this right here will give you the third point for the problem. Getting the answer of negative 13 will give you the fourth point for that part of the problem. So part B has to do with continuity. You probably want to look back at the definition of continuity. I'll write it out for you in this case. So a function is continuous if when you evaluate it at that specific value, it's equal to its limit. Oftentimes you'll see a continuity definition that has right-hand limit and left-hand limit. That's the little one plus and minus with the two. This one, we don't need to really worry about that because we don't have a piecewise function. But we want our limit to be equal to f of 2. So what we need to do is we need to figure out what the limit at x as x approaches 2 is going to be equal to, and that will give us what f of 2 should be. So let's go ahead and find our limit. So the first thing you're going to notice if you put in x equals 2, which you might have been able to figure out based on part A, the first thing you'll notice is that this function will be indeterminate. You'll get a 0 over 0. So what we're going to do, there's actually two ways to solve this out. The first way is to factor and then cancel out factors. That works just fine. The second way is going to be to use L'Hopital's rule. I think probably most people like that one better. So I'm going to take the derivative of the numerator, and I'm going to take the derivative of the denominator, and then I'm going to substitute in 2. And when you do this, you end up getting 11 over 8. And that's actually my answer for this one. So in order, it says to justify your answer. Actually, everything I wrote down here might be enough to get full credit for this. But just in case, I'll write a little explanation. So in order to make f continuous at x equals 2, f of 2 should be defined as 11 over 8, which is the limit as x approaches 2 of f of x. So in order to get full credit on this problem, you need to use the limit of f of x as x approaches 2, and then you need to get the right answer with justification. Not sure where that 8 went, but those are just the two things that you need. You might need less justification than what I have. If you put everything in blue, you probably will get full credit. But just in case, it's always a good idea to write out a sentence explaining what you did. So the last part of this question is looking for the value of x where f has a discontinuity due to a vertical asymptote. If you remember, this actually is something from pre-calculus. A vertical asymptote is going to occur where your denominator is equal to 0, but it's you need to have it at a point where you don't have a hole in the graph, meaning you don't have the numerator equal to 0. So I'm going to set my denominator equal to 0. If you solve that out, you get that x is equal to positive and negative 2. We already know that there is a removable discontinuity at x equals 2, which means it's a hole. So it has to be at x equals negative 2. That's going to be our value where we have a vertical asymptote. So actually in this question, in order to get full credit, you need to also have an explanation. So easiest way to explain it is that the graph has a vertical asymptote because the denominator equals 0 at x equals negative 2, but the numerator does not equal 0 at x equals negative 2. Keep in mind that if both the numerator and denominator equal 0 at that point, that's going to be a hole in the graph. Since only the denominator equals 0, it's a vertical asymptote.